Hello everyone, my name is Ilya Maximets and this talk is about OVSDB performance and scale related changes made during the last year. The slide deck starts with an overwhelming diagram of how transactions work in different OVSDB service models. It's not entirely relevant for this presentation. The main takeaway is that clustered databases do way more work while processing transactions than the standalone one. And another point from here is that when I'm talking about clustered database in this presentation, I'm talking about clusters of free servers. And here is the OVN architecture overview. Here we have two main databases which are northbound and southbound. From what we can see here, use cases for northbound and southbound databases are different. Northbound typically has a small number of clients, but a higher rate of incoming transactions. Southbound has a lot of clients, such as OVN controllers, and it typically has to store more data. Here's a list of OVSDB performance-related changes that were accepted during the last year, and which I will try to cover. We will take a look at each of them separately. 2.13 latest table will be our baseline, so now let's take a look at the test scenario. Following test will be used to check performance. In this test, OVSDB server is running with OVN northbound schema in clustered or standalone mode. Test sends transactions by invoking OVSDB client application in leader-only mode. OVSDB clients are invoked from 50 parallel shells. This means that we will have at most 50 parallel transactions at any time. Another 100 clients are monitoring the database, receiving all the updates. The test is trying to send transactions similar to what OVN Kubernetes may do. It's trying to simulate the addition of a port and the creation of load balancers. 100 logical switches, one load balancer group, and the address set are created beforehand. And test is trying to consequently add 30,000 ports, it's 300 per logical switch, and 30,000 load balancers, and then remove all of them. In total, it will be 120,000 of OVSDB client invocations. And yes, the metric for this test is OVSDB client invocations per second, not transactions per second. It's just because way too many things are happening besides the actual transaction. For example, the OVSDB client process needs time to spawn, terminate, and parse the arguments. It also connects to the server and requests database records from a server database. This will include the sending of 14 kilobyte northbound schema to the client. Clients may also decide to reconnect, since the connection is leader only, or back off in case of a connection failure. So let's take a look at our baseline performance results with OVS 2.13. Well, unfortunately it's not really possible. Standalone database actually finished the test and the performance results are not very bad. It's about 40 OVSDB client invocations per second, and memory consumption is under 100 megabytes. But the database file size grew up to 53 gigabytes. For the clustered database, it did not finish the test. I just had to stop it because the server ran out of RAM and the disk space. Basically, the projected database file size should be around 70 gigabytes per server, and the memory usage was at about 30 gigs per process at the moment I had to stop it. As you might know, database files are incremental, and every new transaction is added to the file in a file transaction format. Same for the in-memory raft log. What happened is that the fast-growing change log in the database file and the raft log exhausted the disk space and the memory. So let's take a look at these transactions. These are parts of file transactions that are creating ports. And we can see that the first transaction adds one port to the set in a logical switch. The next transaction that is supposed to add one port more actually sets both of them, and so on. The last transaction will set 300 ports, so each file transaction contains the whole new set of values of a changed column. The solution is to store only the difference between all the new versions of a row in a file transaction. And that's what patch marked number 2 implements. The database file format change was made in OVS 2.15 release, and it's not backward compatible, so please follow instructions in the OVSDB documentation for upgrade and downgrade. And here are the performance results for this change. Standalone database actually performed twice as well as in 2.13. Database file size decreased 1000 times from 53 gigs down to 51 megabytes. Clustered database test actually finished. The rate of 13.7 OVSDB-client invocations per second, a reasonable database file size, and RSS under 1 gig per server. That's already something that we can work with. So the next group of changes are JSON-related optimizations. Number 3 is the algorithmic change to speed up the string serialization process by copying data more efficiently. Number 4 is the memory optimization to not hold the bulky JSON objects in memory if we don't really need to do that. For example, database snapshots consist of a big number of small objects that could take several times more memory than the same object in its string representation. And the last but very important change is pre-serialization of JSON cache entries. So this work doesn't need to be done for every client that monitors the database. Since the test that I was using doesn't really have a lot of strings nor stresses the monitor updates too much, we will be using a bit different test here. I call it a 100K test. Everything is exactly the same as with the ports and load balancers, but instead of adding ports and load balancers, we will send 100 kilobytes long transactions containing mostly strings. Transaction will create a port group with 500 external IDs, and each external ID's key and value are 100-byte long strings. So we will create 5,000 such port groups to not waste a lot of disk space. Running the test against versions 2 and 5, we can see about 20% performance improvement in the clustered case and 140% performance improvement in the standalone case. RSS improvements are still not very visible because we are not experiencing database compactions during the test, so the raft log doesn't actually store a big database snapshot. But there is still some performance improvement in memory usage. The next thing to talk about is referential integrity, specifically strong references. For them, it's enough to just keep a reference counter per row. If the value of some reference changes, OVSDB decreases the counter for the old referenced row and increases for the new one. In case the column contains a set of references, it will first decrease the counter for all the references in the old version of a set, and then increase for all the references in the new version of that set. This is not efficient if we have a lot of values in this set and only a few of them actually changed. The solution here is to get the difference between sets and update only the changed references. Fortunately, while processing transactions, we either already know the difference or we are able to calculate it fairly fast. Here goes change number 6. Let's look at performance improvement. By the way, we are back to our normal benchmark with ports and load balancers. We can see 5% performance improvement in a standalone case and a 16% performance drop in a clustered case. Well, the reason is actually that patches weren't applied in order they were developed. At this point in Git history, calculation of column differences could be a bit heavy. Once the next patch is applied, operations will be cheaper, so the performance improvement we were hoping to get from this patch will be actually embedded in the performance results for the next changes. The next pack of changes are optimized operations on sets. It's crucial for OVSDB server performance to operate with sets in an efficient way, because OVM tends to add a lot of things into a single column, like add a lot of ports to a logical switch or add a lot of load balancers to the same load balancer group. We have 3 changes here. Number 7, 8 and 9. 7 and 8 allows us to get rid of extra quicksort and separate copies of all the elements. Now we can just move the memory and basically copy only things that were added or removed. Number 9 is very similar, but also allows us to avoid the extra row copy while applying the column diff read from the database file. Detailed descriptions of all the algorithmic changes can be found in the commit messages. We're not providing it here to save time. And now we have a very significant performance improvement. It's like 33% for a standalone case and more than 5 times performance improvement in a clustered case with the extra 50% memory consumption reduction. The next big effort is deduplication of the strings in OVSDB object. Database usually have a significant amount of strings stored. Copying and storing all of this data is a significant performance issue. Patch number 10 introduces a reference counted structure for storing strings. This removes the need to copy big chunks of memory and also allows us to compare strings very fast, as most of the time we actually compare the strings to its copy. Results are impressive. We have 24% performance improvement in a standalone case and 57% performance improvement for a clustered case, where the number went from 52 to 82. Also, there is a 33% memory consumption improvement. Memory is slightly higher in a standalone case because the actual data structure with additional reference counter is larger than a plain string pointer, and standalone databases are not copying strings that much. Continuing to make the OVSDB server more incremental, we need to optimize reassessment of weak references. Implementation of weak references has the same problem of rechecking the whole set instead of rechecking only what changed, but it's also way more complicated. Though some rework of the way back references are stored allowed us to make the process more or less incremental in the patch number 11. And the performance improvement is about 74% in the standalone case and 140% in the clustered, going from 82 to 197 OVSDB-client invocations per second. While implementing all the previous changes, memory profiling pointed to transaction history that accumulates a big percentage of all the memory allocated in a clustered database. History is a place where all the committed transactions end up for a purpose of the fast resync of reconnected clients. While history is limited by only 100 transactions, if transactions are big enough, 100 transactions can actually hold more data than the whole database itself. That is a problem for the memory usage, and this also makes fast resync not that fast. Patch number 12 will not let transaction history grow larger than the database by introducing the size limit. Performance went down a bit, just because the OVSDB server now frees the memory more frequently. At the same time, memory consumption was reduced by 42% in this case, and this can be even much more significant in a real-world scenario. The next is continuation of the string deduplication work started in the patch number 10. This time we are trying to consolidate the OVSDB string object with JSON strings. This way we'll not need to convert them back and forth and also might save some memory. Number 13 does that by simply reusing the same JSON string structure for OVSDB objects. And the last small patch is to avoid extra unnecessary memory copies while sending data over SSL connection. Comparing performance with patches number 13 and 14 to number 12, we have again a slight memory consumption increase since JSON structure is a little bit larger, but we also have a good 12% performance improvement for the clustered database case. And here is a combined performance chart for every version that I tested. We can see that performance of a standalone database increased by 3 times from OVS to 215 and 15 times for a clustered database. It goes up from 13.7 to 207 OVSDB client transactions per second. Invocations per second, sorry. The chart for memory consumption, for standalone, it didn't change much, only a slight increase due to changes in database data structures. But for a clustered database, memory usage reduced 6 times. And here is the test results for our 100K test for every version that I tested. It also shows some good performance improvement for standalone databases, up to 2.5 times, and for a clustered case, it's about 20%. All these tests had 100 monitoring clients, so they don't represent OVN southbound workload for clusters with different number of nodes. So here is the test results for the same 100K test with different number of monitoring clients. Here we can see that performance actually degrades in terms of number of OVSDB client invocations per second. When the number of clients went up 100 times, the metric decreased 10 times. And still, even with 1000 clients, the invocations rate is fairly decent. We have about 24 invocations per second on a clustered database. There is also a table on this slide where I calculated the volume of monitor updates per second that the database sends at this rate. So we can see that with 10 clients, a standalone database sends 223 megabytes per second. For the clusters, it's 127. And it grows with the number of clients since more data needs to be sent. And actually, the standalone database seems to reach some kind of limit at 250 monitoring clients. It doesn't send more than 1.1 gigabyte a second. Clustered, on the other side, doesn't reach this limit. It continues to increase the amount of data it sends up to 2.3 gigabytes per second. It's about 18 gigabit per second. Okay, but what if you don't want to lose the performance while increasing the number of clients? Here's a solution for you. It's OVSDB Relay service model. It was introduced in OVS 2.16 and probably deserves its own lightning talk. But the main idea is that you can run an OVSDB server which will be a client for a main database cluster, but at the same time it will be a server for actual clients. This way the main database cluster will have only a handful of clients and have great performance in terms of transaction rate. And at the same time, relays will take a heavy lifting of sending all the updates to the big number of clients. The difference between relays and conventional replication is that relays are actually not read-only. So OVN controllers are able to send transactions. For example, they can update port state in a southbound database. Relay server will act as a relay, forwarding the transaction and the reply. See more information about relays in the OVS documentation. And of course, these changes are not the only ones that made it in this year. There are plenty of changes in OVSDB IDL for a client part of the database. Thanks to Dimitru for performance improvements and fixing bugs. There is also an implementation split into 2 separate models made by Ben, which allowed a simpler implementation of relay model. Thanks to Newman for new APIs to check table columns existence. And special thanks to Terry for taking care of Python IDL. There were also enhancements and fixes for the Raft cluster stability. Future plans are to continue with incremental performance optimizations, Another big work item is a database compaction on the background that should be possible at least for clustered databases. Conditional monitoring optimizations. And I actually want to rework the test framework that I used for this presentation so everyone can use it. Make it closer to actual transaction per second metric. And some configuration capabilities enhancements for relays. Thank you for your attention.
Welcome back. Ilya, are you able to join us for some questions and discussion? Oh, hello, Ilya.
Hello.
Hello. It's always good to hear from you. I enjoyed the talk. We have one question from Flavio Fernandez, who says that you talked about a lot of great OVSDB enhancements. He says that he wants her to talk about moving OVSDB out of the OVS repo in the same way that we moved OVN out of the OVS repo. Do you see advantages in doing so for maintaining OVSDB?
So we had already this question on the mailing list, I guess, some time ago, and my general thoughts about it is that we don't really have a big enough number of contributors to OVSDB server, so to split it into a separate project. Basically, it's mostly me and a couple more people and who contributes from time to time. So splitting the OVSDB server to a separate project would be a big burden for maintainership. And I'm not sure if it's really worth it at current stage and the number of contributors that we actually have.
Okay, you're getting a lot of praise in the chat for the performance improvements, and we have a couple more questions here. So Han Zhao asked about one of the details of your tests. He says, do the monitor clients monitor everything, or do they use some sort of conditional monitoring? And are the conditions the same across all the clients?
Yeah, currently in this test, they are monitoring everything. I plan to enhance the test to actually have some kind of conditional monitoring, so it can be enabled to test the conditional monitoring capabilities of OVSDB server.
Great. So here's a question from Frode Nordahl that was actually what I was going to ask about myself. So he says, great job optimizing OVSDB server. Do you have any idea what kind of impact that will have at a high level in terms of the scalability of OVN and its limits?
So basically, this work was mostly driven by performance and scale tests done by OVN team here in Red Hat and the performance and scales team for OpenShift, trying to scale and increase the density of clusters. So yeah, it's showed a good performance improvement. You definitely need to test it for your own, since every cluster is different and OVN Kubernetes is very different from what OpenStack does sometimes. So your mileage may vary, but in general, the overall performance of OVSDB server allows, with its changes, allows to perform way more transactions per second and serve way more clients at the same time, especially with monitor all enabled.
Fantastic. I was hoping you would tell us something like, well, now we can double our potential scale, but I know that's not how it works in practice. There are just too many variables. So thanks again, Ilya, for your work and your talk. And now